Hi everybody, welcome to another video in Calculus 3. We go to 13.3, dot products. Once again, we're still reviewing pre-calculus concept. We haven't done any calculus yet. Right, dot products. The dot product given any two non-zero vectors. So any vectors, but of course it can be zero too, but we define that for non-zero vectors. U dot v, the notation is u dot v equal to the magnitudes of u times the magnitudes of v times the cosine of the angle between u and v. Right. So I mentioned before, the magnitude could be 2 bars on each side or 1 bar on each side. Different books use different notation. Here we use 1 bar. Right. And the angle between two vectors will be from 0 to pi. Right. By this definition, if u is a 0 vector or v is a 0 vector, notice that this is the boldface 0. If we write it this by hand, it will be vector u equal to vector 0, like that. And then v was the same thing. And then the dot product of u and v, if one of them is 0, is equal to a 0 number. So notice that this is a 0 number. Whereas this is a 0 vector. And of course, if one of them is 0, the angle is undefined. Right. Next, of course, if we have u dot v equal to the product of the magnitude times cosine of theta, we can say cosine of theta is equal to the dot product over the product of magnitude. If we want to, we can take cosine inverse and we get back to the angle. So this is the formula of the angle between the two vectors. This formula here. Right. Now, this is the angle between two vectors. So does that matter if it is between u and v, or is that doesn't matter if it is between u or v or u? Right. So we have two vectors, u and v. Of course, the angle from u to v is different than the angle from v to u. Those angles are different, right? However, so even though they're different, but one of them should be positive when it's counterclockwise and clockwise when it's negative. But since cosine is an even function, whether we have cosine of theta or cosine of negative theta is still the same. So cosine is even. Cosine is even. By definition, cosine of a negative is the same as cosine of a positive angle. So in that case, it doesn't matter if it is from u to v or from v to u. It's just an angle in between. Right. Now, that formula is nice and all, but even better way to calculate the dot product is given in this form. The dot product of u and v given in component form is that. By the way, if they only have two components, u1, u2, v1, v2, then we don't have the third one. Still fine. So the dot product defined for any dimensional vectors. So even two non-zero vectors, we can add this important thing here in any dimension. 2, 3, or even higher. 2 dimensions. Right. So that's one thing. And the dot product is equal to this. And in different book, the dot product is referred to as a scalar product because the dot product is a scalar. So meaning that it is going to be a number. Dot product is not a vector, it is a number or scalar. Right. So vectors in any dimension, dot product is a scalar angle between two vectors, and the angle in between doesn't matter if it is clockwise or counterclockwise, doesn't matter. So we have three scenarios here. When they have 90 degrees angle, the dot product is equal to 0. So when it's 90 degrees, the dot product is equal to 0 because cosine of 90 degrees is equal to 1. Sorry, cosine of 90 degrees is equal to 0. That's why it's equal to 0. Now, when we have 0 or pi, meaning in the same direction or the opposite direction, cosine of 0 is 1, cosine of 180 degrees is negative 1. So in those cases, we have one of them, cosine equal to 1 and cosine equal to negative 1. Right, so that's what we have. Two vectors u and v are orthogonal if the dot product equal to 0. By the way, from this section and the next one, every single details is very important, so we have to pay attention. It didn't say that two non-zero vector, right? It just said two vectors, and did not say any dimension or anything. But so we say orthogonal is where the dot product equal to 0. This is the only definition about orthogonal. Right. So the zero vectors, by definition, is orthogonal to all other vectors. So that's why in here we don't put non-zero here, because zero vector orthogonal to every other vectors. In 2 or 3 dimensions, two non-orthogonal vectors are perpendicular. So loosely speaking, it is called perpendicular. And then you say, why don't we just call it perpendicular? Well, remember, vectors is not a line. When we have two lines perpendicular, it have to be like this. But the vector can be somewhere in here, somewhere out there. And because vector has no location, so we can move so that it will be perpendicular. But in general, the vector can be like this, and we say they are orthogonal. Meaning we can move so that it will form a 90-degree angle. Right. But other than that, to find the dot product is very simple. I prefer to find all the dot product using this form. So we're going to need to write the vector as the component form, and then just do the dot product. Will be that the sum of the products of components. Right. So vector u dot vector v. U, we have 2 for the first component, negative 6 on the second, and there's no k, we have 0. Dot product with vector v, 12k, so there's no I, no thing on the first component, no thing on the second component, and 12 on the second component. So dot product, the sum of the products of the component, 2 times 0 plus negative 6 times 0 plus 0 and 12 times 12. All of that is 0. So because the product equal to 0, we say they are orthogonal to each other. Right, so simple enough. Right, u is 2 and 1, and v is 0 and negative 3, so that's straightforward. So dot product works for 2 or 3 dimensions, or even higher. If we have to do the dot product of like 4 dimensions, still work. It's still defined the same way. 1 times 5 plus 2 times 6 plus 3 times 7, 4 times 8. But here we only have 2. So 2 times 0 plus 1 times negative 3. Right. So that product's pretty straightforward. It's easier if we write in the bracket notation. Right, now find the angle between them. The angle between two vectors is given by that. So angle between two vectors, we have cosine equal to the dot product over the product of the magnitude. So cosine theta dot product of magnitude the dot product 2 and -1 v 1 and 3 and the magnitude of u square root of 2 square plus -1. It's a plus in the middle, right? Right, 2 times -1 plus -1 times 3 and then square root 2 square 4 1, so square root of 5 and square root of 10. Let's put that in a calculator. Fraction, we have 2 and -3 on the top, so just -1 on top, and square root of 5 square root of 10, and so we have that. And then we take the cosine inverse. It's easy. Usually when we use the inverse, I prefer to use in degree mode, so to get a better sense of what the angle is. So cosine inverse of that result is 98.13 degrees. Right, so I have 98, negative 0.1414, and so theta equal to cosine inverse negative 0.1414 is 98.13 degrees. So it's simple enough, just very straightforward. Just be careful. That's all. Right. Next, we have the angle between two vectors here in 3 dimensions. Right. We do the same thing. Cosine of an angle between two vectors, the dot product over the product of magnitude. The cross product, 2 times -1. Yeah, just put in the numbers. -1 times 0 and 3 times 3. Two square, negative square, and 3 square. Negative square, 0 square, 3 square. Right. Of course, I can just put the whole thing in a calculator, but so -1, 0, and 9, -2, 0, and 9, -2 and 9, 7. The bottom, 2 square, 4, 9, and 1, 4, 9, and 1. That's 14. And 1 and 3, so that's 10. So just have that. So fraction, we can just put cosine inverse of this, but I'm just going to do 7 divided by square root of 14 and square root of 10. So that much, and then cosine inverse have 53.73 degrees. So I've just said theta equal to cosine inverse 7 square 14 square 10 53.73 degree. So simple now. That's the angle between two vectors. Right. Now properties of the dot product. First, u dot v is the same as v dot u. Well, that is obvious because remember we did say cosine is an even function. An even function, cosine of positive theta or negative theta, it doesn't matter. So in that case, we say u dot v is the same as v dot u, and then we have other properties. Right. Now this is a little more important. Orthogonal projection of u onto v denoted projection of u onto v where vector v is not equal to 0 is given by this long-winded formula. Right. So what actually is if we have the vector u and the vector v, what we do is we have the flash line here and we put all of the light, suppose it is parallel to it, and the shadow of vector u onto v is called the projection of u onto v. So if the projection down, vector u will become here. So this part is projection, don't need to say it, of vector u onto vector v. Right. And the formula is that. Usually we stick with this formula here, but where's that formula come about? So let's first say we have the vector v and we have the vector u like that. We wish to find the projection, and usually it is orthogonal projection, but when we just say projection, we actually also mean it's just orthogonal projection. So when we do that, the projection onto it is going to be this part here, right? So this part in the formula we define two things. First, if we only talk about the length of this portion only, if we talk about the length only, then we call the scalar. This length is scalar of vector u onto vector v. And the way we do that is if we have the angle between two vectors, this is we can say cosine of theta is equal to adjacent, which is the scalar component of u, scalar of u onto v divided by the magnitudes of u. So multiply, we have the scalar of u onto v is equal to u times cosine of theta, and theta of course the angle between two vectors. Next, the angle between two vectors will be given as u dot v over the products of the magnitude, and we can cancel out that. So in that case, we can say the scalar component is going to be uv over v. The dot product over v. Right, that's only the length now. If we want the actual vector, we have to multiply by the unit vector in the direction of v. So from here, we have unit vector in direction of v is vector v over magnitudes of v. And so we just take the length, multiply by the unit vector in that direction. So multiply this together, we have projection of u onto v equal to dot product scalar of u onto v times the unit vector in v direction. And so just multiply this together, we have the dot product, magnitude, and then over v, and then the unit vector in direction of v. So put together we have u dot v, and then over the dot product of v. So then you say, why do we have the v? Why do we have in here we have v, magnitude of v times magnitude of v times is equal to v dot v. Well, that's easy. When here we should say, after this the definition, we can say v dot v equal to what? Magnitudes of v times magnitudes of v. The angle between v and v is 0 degree, right? And cosine of 0 is 1. So that's why the dot product of v and itself is equal to the product of the magnitudes, or the square of the magnitude. So that's why when we have the dot product, we have the magnitude square can be written as dot product. That's why we have the dot product at the bottom. So as mentioned before, usually if we ask for the projection, we're going to use this formula. And if we want the scalar component, the scalar will be that. Right. Now, let's look at the first example. Find the projection of u onto v and scalar of u onto v. Actually, we should do this first, and then we do the others, or we just do that part. Right. So, very simple. Scalar of u onto v is going to be the dot product over the magnitudes of v. So we have 4 and 2, dot 4 and 4 over the magnitudes of v, magnitudes of this, 4 square, 4 square. Right, 4 times 4, 16, 2 times 4, 8, so it'll be 24. And then square root of that, 16 and 16, square root of 32. Square of 32, if we can rewrite that, it's going to be 4 square root of 2. So simplify this, we should have 6 over square root of 2. Or even divide that, we should have 3 square root of 2. Multiply square root of 2 top and bottom. Square root of 2 top and bottom, we have square of 2 on the top, 2 at the bottom, cancel, so 3 square root of 2. Right, so that is the scalar. Next, the projection of u onto v. is the dot product over the dot product of v and v. Either we write that or we can just say magnitude square. Yeah, those two are equivalent. Yeah, 1, 2, and 3. Those all of them are equivalent. Right. So put this together, we will have 4 and 2, 4 and 4. Of course, we can just use this formula, but I just want to use that. 4 and 4 dot itself, and whatever we have here is a number multiplied by v, which is 4 and 4, right? So that would be 16 plus 4, 16 and 4, 16 and 8, 24, and then 16 plus 16 will be 32, and then 4 and 4. 24, 32 cancel out will be cancel by 8, 3/4, and 4 and 4, so be 3 and 3. Right, so the orthogonal projection is going to be vector 3 and 3. Let's see how it works. First, the vector u, 4 and 2. For the x2 and the y sort will be this. Vector v, 4 and 4. Then we're trying to find the projection of u onto v. So we just draw the 90 degrees angle from there. And the shadow of u onto v. So this is going to be the projection of u onto v. And of course that will be 3 and 3. Right? So if we want to determine this vector here, it's going to be u plus whatever that is equal to the orthogonal projection. So orthogonal projection is here. Will be that one. Right. Now we'll do the same thing for 3 dimension. Scalar of u onto v. Scalar component of u onto v is equal to the dot product over magnitudes of v. Two, -1 and 3, dot, -1, 0 and 3, over magnitudes of v, -1, 0, magnitude so I have -2, 0, and 9, -2, and so that will be 7, right? -2. That look familiar. That sound familiar. Oh yeah, we did that. 7 over. That's 7. That product is 7. Right, and the magnitudes of that is square root of 10. So that is the scalar component. Now the projection of u onto v is going to be the dot product over the dot product of V times vector V. Notice that there's nothing in here. Right. So we have, I'll just write everything again. V dot V and then times V. We did the dot product already, which is 7. And when we do dot product of V with V, it's going to be the square of this, so it'll be 10, right? Or we just do -1 is 1 plus 9, so it's 10. And then times -1, 0, and 3. So that gives us -7 over 10, 0, and 21 over 10. Right. Now we have an application work. Let a constant force be applied to an object to produce a displacement d. So both of them are vectors. That's why this is bold-faced. If the angle between F and D is theta, then the work done is equal to this, which is dot product. Right. Now just some physics behind what kind of unit we're dealing with. The standard unit, second Newton F equal to ma. So mass times acceleration. Actually, force is a vector, acceleration is a vector as well. So in terms of units, force is equal to unit for force is Newton. I'm talking about the system, the standard international system of units. Mass is kilograms. Acceleration is displacement over times, so it's going to be meter over second square. So 1 Newton is equal to 1 kilogram meter per second square. And then in this case, what we have is work is equal to force times distance. And then cosine has no unit. So in this case, the force is going to, unit of force is Newton. And unit of distance, a standard unit is meter. Cosine has no unit. And in physics, we define that to be a joule. Abbreviated by the capital J. Of course, N is Newton. So that's just a standard unit. Of course, if we use an English system, that will be foot, pounds, and a lot of different things. But just keep with the standard system. Right. A force of 3, 3, and 2 move an object from P to Q. What is the work done by the force? To get the work, we need the force and the vectors of movement. Like we move from where to where. So first we need the vector PQ. That will give us the vector D. To get vector PQ from 2 points, we're going to take Q minus P. Right, Q is 6. Like I said, the notation can be relaxed. But if we use a point, use parentheses. 6, 6, 0, minus 1, 1, 0. That's easy. 5, 5, and 0, right? But we're going to put that in the vector notation. 5, 5, and 0. And now the work done, it's just the dot product of the force, dot product with the vector. The force is 3, 3, and 2. dot with 5, 5 and 0. So we will have 3 times 5 plus 3 times 5 plus 2 times 0. That's 15 and 15, so that will be 30. Right. Since we use Newton and all other units, the result of work is going to be joules. So 30 joules. Notice that we don't need to find the angle between them, but if we do, it's 25 degrees. Not really important. Right. Just do the dot product, and that's it. Right. Next, we have a very common application in physics called the inclined plane. So we have a plane with an angle theta with the horizontal surface. We have an object, we have a mass that's sliding down that. So the reason the block or the mass here is sliding down because it has a weight, and when it have the weight, due to gravity, it will point straight out. This is called the force, gravitational force, F of G. I'm not going to write the weight because weight is also W, so we're not going to do that. So that weight can be decomposed into two components. The first component is called the normal component. That make it stick to the plane, and the other one make it slide down to it. Of course, we can use orthogonal projection. We project this into this or that, but we just use the angle and use cosine and sine. That will be a lot easier. Notice that parallel component of F, let's just say this is F1 and this is F2. So we say the gravitational force is equal to the force in the second, that is normal to it, plus the force parallel to the plane in vector form. So let's see if we have this 10 pound. We take like that. We usually use the international system of unit, but pound is not. So a 10 pound block rests on the plane inclined 30 degrees. So it's like this. I'll find the components of gravitational force parallel and normal to it. So it's easy, right? We have the force here, and of course we can write in terms of orthogonal projection. It's not at all, but we don't really need to. Simple trigonometry will do the trick. So I will write. Okay. Let's do the horizontal plane. And make 30 degrees. Actually have a projector here, so let's get technical. So that is the plane, 30 degrees. However, I'm not going to draw a block. In physics, what at this point we call it a point mass, meaning that consider the mass is located at one point, so we don't have to worry about this, because theoretically the gravitational acceleration due to gravity of that point on the top is different than the point at the bottom, right? Because that point on the top is further away to the center of the earth than this one. So technically the acceleration due to gravity will be different g. Yeah, but that's it. Just assume that it is just one point mass. The weight, of course, points straight down. For the force, gravitational force. and this is 10 pounds. Yeah, I'm not going to write 10 like that. Oh, if we want to, we can write it goes straight down, right? So nothing left and right, but going down 10, negative 10. So we can write that vector as like that. Right. Then we will draw these coordinates. So usually in this type of problem, we will draw the coordinate. It's not traditional xy coordinate. It is depend on the inclined plane. And we just do like this. And then we form, again, 90 degrees angle projection in here. And so we can decompose this into two components. One of them is normal to it. Let's call this is 1. Also, we call the projection of V onto F. A projection of F onto V, sorry. Actually, it's not this one. And then projection of F onto V is actually this one. And if we call this is the plane is vector V, so F2 is projection of F onto V. Right. But we don't even need that. This is 30 degrees angle, right? Find the components. Oh, actually we want a component, so actually that takes some works. If we just want to find the force, that will be easy. We just use cosine of 30 degrees, and that should be easy, right? Oh, actually, we don't need to. So in that case, we just say the force is the magnitudes of F1 and the magnitudes of F2. We don't need to write this as a vector. We just need to write that the magnitudes of those vectors. Right, the magnitudes in that case, we just do that. Just do that instead of the projection. But even easier. If this is 30 degrees, this is also 30 degrees. Right. So the magnitudes of the vector F1 is adjacent to 30 degrees, and the gravitational force is 10 pounds. So that's 10. So we just say that is adjacent is equal to hypotenuse times cosine. So hypotenuse times cosine of 30 degrees. So 10 times cosine of 30 degrees, which is square root of 3 over 2. So 5 square root of 3. And that is the magnitude of force, so the unit will be, actually we use pounds here, so that's still pounds. And then F2, either this or that, is going to be the gravitational force, 10 pounds. This is opposite to the angle. Sine 30 degrees 1/2, so it will be 5 pounds. Right. So that's pretty much it. So that is the dot product. Very simple. So what can we do with dot product? Okay, dot product definition works for any vectors, any dimension. Angle between two vectors doesn't matter from U to V or from V to U. Dot product is a number. Right. With dot product, we can determine the angles between two vectors, and then we can do the orthogonal projection of U onto V or scalar component of U onto V. And an application for dot product is work. Right. With that, we finished section 13.3. See you in another video in Calculus 3. Thank you for watching.